Yes, as Alan said, I'm Steve Schell. I'm the CTO at Heliogen. And I want to focus my discussion today on the heliostat itself. My title is Heliogen's Advanced Heliostat Field for Carbon-Free High-Temperature Heat. I thought this would be a good topic to follow on to Lars's interesting discussion about his high-temperature particle receiver. So Wes touched on this briefly, but I wanted to start with a quick overview of the different types of solar concentrators for solar thermal energy. On the left, I showed two different line focus systems, the parabolic trough and the linear Fresnel. And on the right are the two different point focus systems, parabolic dishes and heliostat fields. The key parameters to differentiate between what these different systems are capable of is the concentration ratios, where the linear systems on the left will achieve relatively low concentration ratios of around 100x, whereas the point focus systems can go much higher, say maybe 2,000 times concentration, something on that order. The concentration ratio will lead directly to the achievable temperature. So the systems on the left would be more appropriate for lower temperatures, maybe 400 degrees centigrade, while the point focus systems on the right would be appropriate for high temperature applications, such as what might be interesting to the audience. And then, of course, the key differentiator between the two point focus systems, the parabolic dish and the heliostat field, is the achievable power level, where a parabolic dish might be appropriate for powers up to tens of kilowatts thermal. Heliostat fields can go much larger, tens of megawatts, even potentially hundreds of megawatts thermal. So for high temperature, large scale industrial applications, it's really the heliostat field configuration that should be of greatest interest, and that's what I'm speaking about this afternoon. So talking about what is required in a heliostat to have high performance at these high temperatures, it's really all about the optics. The capability of a heliostat field to achieve high temperature efficiently is directly related to the concentration ratio that it can achieve, meaning how many times are we multiplying the intensity of the sunlight. So the higher the optical accuracy the heliostat field achieves, the higher the concentration ratio, and therefore the higher the efficiencies, particularly at high temperatures where some of the losses in the system can start to increase quite rapidly at lower concentrations. So touching briefly then on the different sources of optical error. So when we talk about the optical accuracy of a heliostat field, what am I talking about? There's really four main types of optical error. There's mirror shape error. This is just deviation from the ideal shape that you would want your mirror to be. And obviously any deviation from that shape will reflect sun rays into an imperfect direction and tend to defocus the beam from that heliostat. There's also tracking error, meaning the heliostat orientation is less than ideal, and that'll orient the beam into a non-preferred direction. There's something referred to as canting error. Now this refers to the relative alignment between multiple mirror facets on the same heliostat. So traditionally, heliostats tend to be quite large, too large to produce with a single glass mirror, and so there's multiple mirror facets. As you can imagine, the relative alignment between those facets becomes very important, and any errors there can defocus the beam as well. And then last is something referred to as off-axis aberrations. I'll talk about this a little bit more later, but it basically refers to the beam changing shape as the sun moves. So the point of this is that to produce a really high performance heliostat field, again, one that's appropriate for high temperature applications, you really have to address every single one of these sources of optical error in the heliostat field. So with that, I'd like to introduce the HelioMax. This is the first heliostat system that's specifically designed for high temperature industrial process heat applications. The photograph that you see here is Heliogen's test facility here in Southern California. We brought this online in the second half of last year. It includes 400 heliostats, and I'll talk a little bit more about how they're designed and controlled. So referring to each of those sources of optical error in sequence, with regard to the mirror shape, the HelioMax includes an all-glass sandwich panel-like construction for the mirror assembly. This achieves several things. So one, it gives us extremely good shape accuracy. So the way we manufacture these glass panels, we bend the glass into a very specific shape, and it holds the shape quite well when it's complete. It achieves very low cost, because glass is actually a very cost-effective structural material, and the adhesives used are commodity adhesives. It gives us really good stiffness, so we don't get optical errors when the heliostat is subjected to loads, wind loads, gravity loads, things like that. And because it's entirely constructed of glass, we don't have any concerns about differential thermal expansion, so we have a nice consistent focus over a range of temperatures. We don't get any defocusing behavior on a hot day versus a cold day in the field. For our demonstration project here in California, we built a mirror measurement system. This is a laser autocollimator-based measurement device, and we were able to achieve better than 1 milliradian accuracy on the shape of these mirrors. And I think it's important to note that that's even true at very short focal lengths. As you can imagine, the shorter the focal length you're building with a mirror like this, the more you have to bend the glass, the more curvature is required, and bending a thin piece of glass aggressively tends to cause it to ripple and do all sorts of undesirable things. But we were quite happy with the result of better than 1 milliradian, even at the shortest focal lengths in the field, which in our case were less than 20 meters. They were quite short. So moving on to the next source of optical error, we'll talk about panting. Addressing this is somewhat straightforward in some ways. We simply make the heliostat out of a single facet. So on the left, you see a traditional large multi-facet heliostat. This photograph was taken at Solar 2 back in the 1990s. On the right, you see the first few Heliomax heliostats that were being installed in our test field, and as is readily apparent, they're each only a single facet. That seems like a straightforward design choice, but of course it means that to get the same collector area, we require a much larger number of the heliostats, and that requires a unique control system, which I'll talk about in a little bit. Looking at off-axis aberrations, as I mentioned before, this is an optical effect that defocuses the beam as the sun moves. So you see on the left, when the sun is sort of optimally oriented relative to the heliostat and the focal point, the focal spot can be quite small. Whereas when the sun moves across the sky and the heliostat has to reorient itself accordingly, the beam tends to be defocused. This is an effect that is really inherent to any kind of mirror that is of fixed shape, but what we can do is make it smaller. So it turns out the smaller the mirror, the smaller this effect becomes. So for some comparisons, I've brought up a single heliostat in Heliogen's optical modeling tool that we use to design heliostat fields. One heliostat on the left is the Heliomax small heliostat, and the one on the right is kind of a generic large heliostat that I created. It's not any specific competitor, but it is a 120 square meter heliostat, so something that would be more traditional in a large CSP plant, like the one that Wes showed in his presentation months ago. So as you can see, at noon, when the sun is relatively well aligned with the tower, the beams are somewhat similar, and the majority of the flux is falling within the receiver aperture in both cases. But if we look at what happens on the same day at 9 o'clock in the morning, you see the beam from the Heliomax has barely changed at all. It was essentially an imperceptible difference, while the large heliostat beam has become significantly defocused, and it's now about 10% of the energy is now falling outside of the receiver aperture. So this can be quite a large effect. So moving on to tracking error, I think it's important to first take a step back and look at how heliostat fields are normally controlled and how their tracking is typically optimized. So the existing state-of-the-art in heliostat fields is described here, and it's a multi-step process to calibrate and track a heliostat field. So you first, of course, install the heliostat, then they go through this calibration process where one at a time, a heliostat orients its beam to this target screen that's typically mounted on the tower just below the receiver. Sometimes they use the tower itself, but regardless, there's a target that the beam is placed upon. cameras mounted at ground level look up at that target and assess how well centered the beam is relative to where it was commanded to go, and they make small offsets to optimize that tracking. Now, this process needs to be repeated over many different sun positions, meaning you have to wait for the sun to move across the sky, not only over the course of the day, but over actually months to kind of fill out the full space of where that sun could possibly go. So one by one, these heliostats are tracked, calibrated, and eventually, like I said, over weeks or months, you can gather enough data to fully calibrate the mechanism of that heliostat. So you build up a kinematic model with several optimized parameters to try to describe the behavior of that heliostat. And then from then on, you operate the field using those calibrated parameters and just make the assumption that it's therefore perfect from then on. So Heliogen has done something very different from this, and we're the first in the world to commercialize a closed-loop tracking system for heliostat fields. So what do? Instead of the calibrate, then track open loop system that I described before, we use what we call the heliostat observation system, or HOS, which uses several cameras that are mounted on the tower, kind of near the receiver, but very importantly, they're not in the beam, so these cameras are not taking high heat flux. They look down at the field, and we use a computer vision algorithm to estimate the beam position coming from every single heliostat in real time all the time. And those measurements are then used in a closed loop control system to make small tracking corrections as necessary to optimize the tracking of the heliostat field continuously in real time. This is the first in the world, as I mentioned, to do this. The photograph that you see on the right is from our test facility. I've put circles around the cameras. The two at the top are usually pretty easy to see, but the two below are kind of hidden under the deck. So some benefits of closed loop tracking, because there are many. So one, as you can imagine, the tracking accuracy is improved because we're watching the heliostat beams all the time, making small corrections. We can achieve tighter tracking accuracy than what can be done open loop. You eliminate that calibration time, so we completely eliminate that multi-month process of calibrating the heliostat field. With the HOS-based system, you really can install a heliostat field one day and start tracking it on the receiver the next day. We also eliminate the need for recalibration, so there's no ongoing operations and maintenance expense at the plant associated with recalibrating heliostats over time. We identify problems very quickly because they are being monitored continuously all the time. If there is any kind of problem heliostat, if one is having mechanical trouble and is not able to track, or the tracking accuracy becomes poor, the system will automatically detect those things and bring them to the attention of the plant operator for maintenance. It automatically compensates for changes, so if there's some kind of ground settling over time, the tower sways slightly and when it's heated by the sun on one side or something like that, all of these things are sort of automatically compensated for. And of course, all of that, the net result is that it reduces the capital and operating costs of the plant, which ultimately, of course, is the thing that matters. So to try to put a little bit more numbers to that statement, I brought up in our modeling tool two different fields. I designed one heliostat field using HelioMax heliostats, and another one using, again, those kind of typical generic large heliostats. And both of these fields were designed with the same design inputs. So 10 megawatt thermal at the design point, looking for high flux, so 1,000 kilowatts per square meter average over the receiver aperture. This would be a relatively high flux level that would be appropriate for a receiver like the one that Lars just showed, and a 40-meter tower height. So the first thing that jumps out, knowing that these two fields are drawn to scale, is that the heliostat, the HelioMax field is quite a bit smaller. So we're able to make these fields very compact using our system, so we require less land area for the same power delivery. But beyond that, let's get into some more comparisons. So looking at the flux profiles that are delivered at the design point, you see the HelioMax on the top and the comparative typical field on the bottom. And what I've done is I've shown a linear scale for the color gradient on the left and the log scale on the right. Looking at the left on the linear scale tends to identify peaks very easily. So you can see that we're achieving about 10 megawatts per square meter peak flux with HelioMax. So very, very high, which again, for a cavity receiver like the particle receiver that was just shown, this can be a very beneficial mean. Whereas the typical heliostat field is achieving something on the order of 2.5 megawatts per square meter peak, so about 1/4 as much peak flux. And directing your attention to the right, the log scale can be useful to understand the spillage or how much of the light is missing the aperture. So you can see it's pretty readily obvious that there's of course some spillage with the heliumax field, but it's greatly increased in the case of the typical heliostat field. And I'll just comment that these are at the design point when the optics are sort of as good as they're going to get. The off-axis aberrations that I mentioned will actually exacerbate that spillage on the lower right side at any other time of the day when the sun moves around.
Steve, 5 minutes.
No problem. Thanks, Ellen. So seeing how that all compares a little more quantitatively, let's start comparing some KPIs. So looking at the field optical efficiency, we see that heliumax has about a 9% advantage over the typical field. The intercept efficiency, meaning what percentage of the light is making it into the receiver aperture, we have quite a large advantage, about 20% in this case. That results in a difference in collector area required, so meaning just how many heliostats or how many square meters of collector do we need to achieve the target power. We have about a 15% advantage with heliumax. And the land area required, as I mentioned before, is very significant difference, just about half. And even with all of that, the typical field is still slightly underperforming, about 9.5 megawatts thermal being delivered. This is a target of 10, while the heliumax was slightly overperforming at 10.5, about an 11% difference there. So what does that turn into in economics? So if we assume the U.S. Department of Energy's 2020 target of $75 per square meter, I've sort of leveled the playing field on heliostat cost, even though I'll comment that our heliumax roadmap gets us pretty significantly below the $75 per square meter price. So that's a number we're very comfortable with on large projects today, but it's going to continue coming down beyond that. But that's a 15% advantage. Looking at the land cost at a nominal $7,500 per hectare, that saves us about $50,000. So the total cost difference, we see about an 18% advantage with heliumax. And then adding to that, the fact that we're getting 11% more power out of it, the net result is about a 26% reduction in the cost per delivered kilowatt thermal. And with that, I will conclude my remarks. Thank you very much.